Everybody, Justin here from chemistrynotes.com, and today is our third video on section 8, chemical bonding. And today we're going to talk about ions, ion sizes, and ion electron configurations. So let's get started. At the top of page 1 of our notes, ions, electron configurations, and relative sizes. So there's a few things we need to mention here before we get into some sample problems. It says generally a cation, and we're going to kind of recognize cations as X plus. Cations are smaller than their parent atom. Now, oppositely, anions, or X minus, anions are larger than the parent atom. So a cation is smaller than its atom, and an anion is larger. So schematically, we can draw that with this less than, greater than symbolism. So on the far left is X plus, that's a cation, and in the middle is the parent atom, and on the far right, we have the anion, which is given the larger size of X minus. Okay, so cations lose an electron, so the electron cloud gets smaller, and anions are going to gain an electron, so the electron cloud gets larger. All right, so let's switch gears now and let's write about electron configurations. So the example problem says write the electron configuration, the noble gas notation, and the orbital notation for the following. And those guys are O minus 1, Na plus, and Fe2 plus. Well, we have O minus, Na plus, and Fe2 plus. So to draw the electron configurations, really, it's no different than drawing electron configurations for atoms, which we've already discussed. Really, we just have to figure out how many electrons there are. So to do this, we really only need to know the number of electrons for each ion. First one is O minus, okay? So O has an atomic number 8. That means it has 8 electrons, assuming the oxygen we're talking about is a neutral atom. Now we have to add one more electron for that minus 1 charge. So O minus has 9 electrons. Now, we learned in the diagonal rule that the way we fill electrons are 1s2, 2s2, 2p5. And why not throw in the number of valence electrons while we're at it? 7 valence electrons. Those guys, the 7 valence electrons, by the way, were the 2s2, 2p5. Now for the noble gas notation. Sometimes it's called noble gas configuration. Well, we back up to the nearest previous noble gas, which is helium. So bracket helium, 2s2, 2p5. And the last one they asked for was orbital notation. So 1s2, 2s2, 2p5. And if you watch that slowly, you'll see how I filled the electrons. All right, second one is Na plus. So what we do is we go to sodium on the periodic table. We notice that its atomic number is 11. That means it has 11 protons. We assume it's neutral, so it also has 11 electrons. Now that plus charge means we've taken away 1 electron. So we have a total of 10 electrons. So the complete electron configuration is 1s2, 2s2, 2p6. So the n equals 2 level is 2s2, 2p6. That's where my 8 valence electrons are. Now they also want the noble gas configuration, so I have to do that. I back up to the previous noble gas, He, 2s2, 2p6. Now 10 electrons also lies right on neon. So I guess technically you could use either of these guys as your noble gas notation, but I like the first answer a little bit better. Depends on what class you're in, what your professor or instructor asks of you. Okay, Na plus orbital notation, 1s2, 2s2, 2p6. And if you watch that video slowly, you'll see how I fill all the degenerate orbitals one at a time before I come back. So for those 2p orbitals, I fill them up singly, come back, fill them up doubly. All right, next page of our notes, Fe2 plus. Well, we go and we find Fe, atomic number 26. It's got a 2 plus charge. That brings my electron count down to 24. Now, for those of you who remember, 24 electrons and 29 electrons, those are the two exceptions to the diagonal rule. Chromium is atomic number 24. It's got 24 electrons, just like Fe2 plus. So I have to be careful when assigning electron configurations for Fe2 plus. So the complete electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, careful, 4s1, 3d5. All right, so noble gas notation then, I back up to the previous noble gas on the periodic table, which is argon, and then I just kind of go from there, 4s1, 3d5. Now I haven't written down the number of valence electrons here, but the answer to that question would be 1, the 4s1 electron. All right, lastly, orbital notation. Drawing out all my orbitals. I got my 3 degenerate 2p's, my 3 degenerate 3p's, and my 5 degenerate 3d orbitals. Fill everybody up accordingly, according to Hund's rule. 4s1, 3d5 at the end. All right? All right, let's come back to the topic we talked about at the very beginning of today's notes, and that's relative size of ions. So that's what the next example asks. It reads, order the ions from smallest to largest ionic radius. Li plus, Na plus, K plus, Rb plus, and Cs plus. Well, these guys are all group 1, okay? And we've just removed an electron from everybody in group 1. So what we have to recognize is that these guys are all group 1 cations. And if you remember from the very first trend, periodic trend we talked about was ionic radius or atomic size, ionic size, whatever you want to call it, whether it's size or radius. We learned that going down a group, size increases. So I just have to list them from top to bottom on the periodic table. Li plus is the smallest. We go in order with Cs plus or cesium cation being the largest. Now B is a little bit different. Ba2 plus, Cs plus, I minus, and Te2 minus. These guys aren't in the same group, but they do have the same number of electrons. So all 4 ions have 54 electrons. So you would think that the electron cloud is the same size for all of them because it's got 54 electrons. Well, who's the better magnet? In other words, whose nucleus has the most protons? The more protons in the nucleus, the better magnet you are at drawing or pulling those electrons in. So that's what we need to take a look at. So who has the highest or the largest atomic number? And the second bullet point there says all 4 ions have 54 electrons, so their electron clouds would be the same size. Double underline says, however, each ion has a different amount of protons in its nucleus. In other words, a different atomic number. The ion with the most protons, in other words, the largest positive nucleus, is going to be the best at pulling or drawing those electrons in and make it smaller. So we have to look at the atomic number. Let me just finish up writing here. It says the ion with the most protons is best at pulling the 54 electrons in toward the nucleus, thus decreasing the size of the electron cloud. All right, so it's a plus-minus attraction. We want the biggest plus to be our smallest. All right, so barium 2 plus is my smallest. Cesium plus is my second smallest. Te2 minus is my largest, and I minus is my second largest. All right, so that's it for today's notes. And if you like the way I do these handwritten chemistry notes. You can see all my general chemistry and organic chemistry notes at chemistrynotes.com. And I'll see you in a couple days when I make the next video. All right, see you then.